So as we begin our module 10.2, we're going to take a look at our plane strain and talk about three-dimensional analysis of strain as well. So objectives within this module, we're going to take a look at the transformations of plane strain, looking at our transformation equations, and Moore's circle now for plane strain. So we're looking at it rather in strain rather than stress now. Then we'll take a look at the three-dimensional analysis of strain, and then talk about the measurements of strain looking at our strain rosette. So as we begin this module, a couple activities we're going to do is first we're going to do a little bit of review, then get into some of the theory of the topics above here and talk about these key equations, some practical applications, and then get into some problem solving together. So continuing on looking at our maximum normal stress criteria right here, what I want to take a look at now is the kind of definition and what this actually is. So the maximum stress criteria, also known as normal stress right here, Coulomb or Rankine criteria. This is often used to predict the failure of brittle materials. So that's what we're going to utilize this for, is predicting the failure of brittle materials. So the maximum stress criteria states that the failure occurs when the maximum or normal principal stress right there reaches either the uniaxial tension strength, or sigma sub t, or the uniaxial compression, sigma sub c right there. So as far as an equation goes, this says that our negative sigma c is less than our sigma 1 comma sigma 2, which is less than our sigma t, where sigma 1 and sigma 2 are the principal stresses for 2D stress. Now graphically, we can represent this here. The maximum stress criteria requires that two principal stresses lie within the green zone predicted below. So again, if two of these lie within this here, we're good. If they don't, then it does not necessarily follow the criterion. So now going back to our graphical representation right here, we can see what we have in this graph here is uniaxial tension right there. So we're just looking at tension. So our S sub yt is our yield strength and tension right there. So we can draw that out on our axis right here. There's our sigma axis. There's our shear axis right there. Now this distance going right here, which is the diameter of that circle right there, this is the principle. This is the fact that our principal Moore circle must rely within these bounds to avoid failure right there. So these are the two bounds right here that our Moore circle, our principal Moore circle, must lie within to avoid failure. So let's just take a look. If we have this right here, we can see now for this example right here that this does not lie within these bounds, so therefore does not necessarily avoid failure. So let's take a look now at Moore's theory and go into a little bit of detail and review of that there. So Moore's theory suggests that failure occurs when Moore's circle at a point in the body exceeds the envelope created by the two Moore circles for our uniaxial tensile strength right here in red, and our uniaxial compression strength right here in blue right there. So in the graph below, we can see the envelope shown in this figure right there. So we can see over here, we have our uniaxial tensile strength right here, our sigma sub t with this red circle right there, uniaxial tension. Then we have over here uniaxial compression with our blue circle right there, our sigma sub c right there like that. So now this left blue circle is for the uniaxial compression at the limiting compression stress right here of our sigma c of that material. Likewise, the right circle in red right here is for uniaxial tension at the limiting tension stress right here, our sigma sub t that we see right there. Now the middle circle on the figure right here, this dashed line, this black dashed line, this represents the maximum allowable stress for an intermediate stress state right there. So all intermediate stress states fall into one of four different categories, which I'm going to show in the following table right here. So each case defines the maximum allowable values for the two principal stresses to avoid failure. So that's something that's important. We're trying to figure out how we can avoid failure. That's going to help us determine that right there. So you can see that again, there's our blue circle, uniaxial compression, red circle, uniaxial tension right there. And now we can see this center right here for our intermediate stress right here, this black dash circle right there. And you see this one right here fits within that envelope. Now, as we mentioned, all these immediate stress states fall into one of the following four categories on this table below here. Now, each of these four cases defines the maximum allowable value of the two principal stresses in order for us to avoid that failure right there. So in case one, both of them are in tension, so our sigma 1 is greater than 0 and our sigma 2 is greater than 0. So in this case here, our sigma 1 is less than our sigma sub t, and our sigma 2 is less than our sigma sub t as well. Now, for our case number 2, both of these are in compression right here. So for compression right here, our sigma 1 is less than 0 and our sigma 2 is less than 0 because it's compression right there. And sigma 1 is going to be greater than our negative sigma sub c, and sigma sub 2 is also going to be greater than our negative sigma sub c right there for compression. Now, for case 3, we have sigma 1 is in tension and sigma 2 is in compression. So sigma 1 is greater than 0, sigma 2 is less than 0. And we have this relationship here that sigma 1 over delta t plus sigma 2 over delta negative c is going to be less than 0. Then we have the reverse case of that where sigma 1 is in compression, sigma 2 is in tension, so sigma 1 is less than 0, sigma 2 is greater than 0, and our sigma 1 over negative c plus sigma 2 over sigma t is going to be less than 1. So we'll get started with the topic of transformation of plane strain. So what is plane strain? Plane strains are the deformations of the material that take place in parallel planes and are the same in each of those planes. Plane strain occurs in a plate subjected along its edges to a uniformly distributed load. It's going to be a uniformly distributed load and is restrained from expanding or contracting laterally by smooth, rigid, and fixed supports. So what we have over here on the left in this diagram is we have plane strain example with laterally restrained by fixed supports. You can see your fixed support right here and a fixed support right there. We can take a look at this. Always want to pay attention to our coordinate system. We can see our x-axis is going along here. We have our y-axis coming up top. And we have our z-axis coming out here. Again, we can use our right-hand rule to make sure, curl up our x towards our y, make sure that our z is in the positive direction it comes out, as it is right there. And we can also see our loads moving, and we can see we have our loads coming along the top here, like this. This is going to be going in our positive x direction there, and we can see some coming down in our negative y direction there. We got these coming up in our positive y direction right here, and these coming in over here in our negative x direction. So pay attention to your sign convention, pay attention to your coordinate system, and make sure that those mesh. So looking at our components of strain now, we have our epsilon sub x, epsilon sub y, and we have our gamma xy right there. And we also see now that our epsilon sub z in our z direction, again going back to that coordinate system we looked at before in our example above here, in our z direction is equal to our gamma zy, our gamma zx, and these are all equal to 0. So all three of those terms are equal to 0. So now let's take a look at an example out here where we're going to consider a long bar subjected to uniformly distributed transverse loads. So pay attention to this right here, uniformly, just as we saw above there, this is a uniformly distributed load up top here. That's something to pay attention to as we're thinking about these applied loads. So now for this case here, the state of plane stress exists in any transverse section that is not located too close to the ends of the bar, which is a different situation to discuss later. So for our example over here, we have this plane strain example. So there is a bar of infinite length in the z direction right there with that infinite length notation right there. That's again eliminates this scenario here where we're not too close to the ends of the bar. So again, we can see there's our x direction right here. We can see our distributed loads coming in on this face right here, going our negative x direction. We can also see we have on the top plane up top here. So this would be our zx plane right there. We can see our loads coming down here and our negative y direction distributed across that there. So as we continue on with our topic of transformation of plane strain, we're going to take a look at a plane strain element. So in this figure here, we can see our plane strain element. Here is our x-axis and our y-axis right there. We can see we have this point Q on our element right there, and we have our delta S and our delta S to the side. So this is the undeformed element right there, and we have our deformed element over here on the right. Well, there's our same x-axis and y-axis right there, and now we can see this deformed element right here. And there's our Q point right in the middle again. We can see we have this angle here. This is pi over 2 plus our gamma xy, pi over 2 minus our gamma xy, and now our side over here, rather than being delta S, is delta S times 1 plus our epsilon sub y. And then down below in the diagram, we have the transformation of plane strain element in undeformed and deformed orientation. So in undeformed orientation, we can see here's our x prime, y prime. There's our undeformed element right here, and there's our delta S, and our Q on our element. And now we can come over to the right, and we can see our deformed element on our new axes right here, our x prime and our y prime axes here. And we can again see this is our element. There's a point Q in the center right there. And now this angle down here is our pi over 2 plus our gamma x prime y prime. Then we have our pi over 2 minus our gamma x prime y prime right here, because we're now on our x prime y prime axes there. And now we can see for our sides, we have our delta S times 1 plus our epsilon x prime and delta S times 1 plus our epsilon y prime. So now let's relate some of these variables we see in our diagrams to the governing equations in our textbook. In particular, look at equations 741, 742, and 743. So for our equation 741, what this does is it uses a couple trig identities to reduce down to this format here and enables us to determine the normal strain in any direction AB in terms of our strain components that we talked about before, our epsilon sub x, epsilon sub y, and our gamma xy. So our epsilon x, epsilon y, and our gamma xy. Now you can also see that we have a theta term here. So the angle theta, what this does is this is the angle between AB and the angle that it forms with our x-axis. So that's what this theta is right here between AB and our x-axis, gives us this value for our theta that we see in this equation 7.41. So now what we can do is we can plug in for our theta. So if we plug in a 0 for our theta here, so this would be our epsilon sub 0, and plug that in for all of our theta terms here, what we find out from equation 7.41 is that an epsilon of 0 is equal to an epsilon sub x. So from there we can also plug in a theta is equal to 90 degrees, so we find out for our epsilon of 90, this is equal to our epsilon sub y. Now we can also plug in a value of our theta is equal to 45 into this equation here, and from that we obtain the normal strain in the direction of our bisector OB. So here's our bisector OB right there. You can see there's our 45 degrees, and that's when we plug in this 45 right here for our theta term into equation 7.41. And that angle again is the intersect between OB and our x and our y axis. You can see it's the same on both our x and our y axes between that angle of our bisector OB. Now if we denote our strain by this epsilon OB now, what we do is we can come up with this relationship we see here in our equation 7.42. Next, what we can do is we can take this equation, our 7.42 here, which we've derived by putting in that 45 degrees for our theta term there. And with this, what we can do is we can solve this now for our gamma xy. So if we solve this for our gamma xy right there, we end up with the relationship that we see down here in equation 7.43. So our gamma xy is equal to 2 times our epsilon OB, which again, this was our bisector over here, our OB right there, minus epsilon x minus our epsilon y. And we saw that relationship there. That's when we plug in theta of 0 and a theta of 90 into our equation 7.41. So we end up with that relationship there. Now, the thing to note is this relationship makes it possible to express our shearing strain associated with a given pair of rectangular axes in terms of our normal strains measured along these axes and their bisector. So now going back to our plane strain element for undeformed and deformed, looking at this on our x, y axes as well as our x prime, y prime axes. Now that we have some relationships for our theta and all of our variables within this, we can do now is we can apply our trigonometric relations used for these transformation of stresses. And this relates to our textbook to equation 7.44 up through 7.49 in the book. So if we take a look at equation 7.44, we can see here we have our strain in our x prime. So there we go, our strain right there, our epsilon sub x prime right there is equal to our epsilon sub x plus epsilon y all over 2 plus epsilon x minus epsilon y over 2. Now pay attention to your sign convention here. This is important as you're going through and solving these equations there. This is times the cosine of 2 times our theta. We come down here, there's our theta. Theta is the difference between our x and our x prime axes right there. It's also the same if we see up here, it's the same relationship or same angles between our y and our y prime axes right here. There's our theta term. This is plus now our gamma x, y, all divided by 2 times our sine of 2 theta right there. So again, these are obtained using some trigonometric relationships and identities. You can go back to the textbook and they go through the derivation that we use, a little bit of a refresher on that. So then this is also similar to what we see here in our equation 7.45 from our textbook, where we have now this is our relationship for our epsilon sub y prime. So now we're looking for our epsilon sub y prime. So we can say we now have this is going to be our epsilon x plus our epsilon y over 2, same as above there, minus. So this is the difference right here. This is minus now our epsilon x minus epsilon y over 2. So you can note the sign convention changes right there between equations 744 and 745. This is still times our cosine of 2 theta, but again, now we have another minus sign here as we're dealing with our y prime component times our gamma xy over 2 times our sine of 2 theta. So the big difference between 744 and 745 is the sign convention here, going from positive to minus, plus to negative right here at those locations. So the last relationship we're going to take a look at is our equation 7.49a. We're looking for our gamma x prime y prime. So gamma x prime y prime divided by 2 is going to be equal to a negative epsilon x minus epsilon y over 2 times our sine of 2 theta plus our gamma xy over 2 times the cosine of 2 theta. So now I want to take a look at Moore's circle for plane strain. We've already looked extensively at Moore's circle for our plane stress. Now let's apply it for plane strain. So as we're going to strain, the equations for the transformation of plane strain are going to be in the same form as the equations for the transformations of plane stress. So we can go back and say that our Moore's circle techniques still apply. The same ones we saw for plane stress are still going to apply for plane strain. So as we take a look in the figure in our top left for our Moore's circle for plane strain, what we can notice here is that on our x-axis now we have our epsilon or our normal strain, and our y-axis we now have our gamma or our shearing strain. So that's going to be the main difference from what we saw for our Moore's circle for stress. So now we can look at this in terms of strain. So we have these different axes here, and we can see that the location here for our center C and our radius have the following relationships here. So we can see that our epsilon average, if we come down here, goes from our point O over here to our center of our circle, or Moore's circles right there, and this is our average strain right there. So that's our given by this relationship of epsilon x plus epsilon y all divided by 2. So we can get that relationship there for our epsilon x, epsilon y divided by 2, and now come up with our average term there. Now for our radius, we can still use the square root of the sum of the squares, and this says that our radius r going from the center at C here out to the outer point of the circle, which would be C to A, C to x, C to y, C to d, C to e, all of those are still going to have that same radius that we've seen before, and this is going to be equal to the square root of our epsilon x minus epsilon y all divided by 2 quantity squared plus our gamma xy over 2 quantity squared. So now let's look down at the bottom left of this figure here for Moore's circle for plane strain, showing our principal strains and our maximum in-plane shearing strain. What I'll focus on here is this angle theta p right here. So we have 2 times our theta p, and this is the angle between cx and our CA right there. Now the relationship we can utilize is shown up here, that the tangent of 2 times theta p is going to be equal to our gamma xy divided by our epsilon x minus epsilon y. And that's just utilizing some trig from the geometries that we can see in that figure there to come up with this relationship. So now we can also see on this figure in the bottom left, we have our epsilon max, our max strain, and our epsilon min, our min strain right here. So there's our epsilon min going from O to B right there, and our epsilon max here now going from O all the way out here to our point A. So that's our epsilon min and epsilon max. What we can see here is that our epsilon max right here, this whole distance, is equal to our epsilon average plus our R value right there. That makes sense. So epsilon average goes right here from O to our center at C, and our radius right here goes from C to A. So adding those two together would give us our max strain. Now for our max min, we have this relationship here that our epsilon sub average, so this goes again from O to C right there, minus our R term from there to there, which is C to B, would just leave us with our OB, which is our epsilon min, or our minimum strain right there. So these equations make sense as we relate them back to our Moore's circle. So now we can see on Moore's circle here, we have this value that goes from our axis down here from point C up to D, and this is 1/2 of our max strain, so in plane right there. So we can say as well, if we want the full max right there, our gamma max or shearing strain right there, this is going to be actually from E to D, that full length here. So that's going to be 2 times our diameter right there. So 2 times our radius is equal to multiplying this right here by 2 there. So we have this relationship. If we multiply through by 2, this is now saying that 2r is equal to the square root of the sum of the squares of epsilon x minus epsilon y squared plus our gamma xy squared there. And that'll give us that value for 2r, which is our max shearing strain there. So now in previous sections, we've shown that there are 3 principal axes that exist such that the perpendicular element faces are going to be free of shearing stresses. So we can go over here on the left now in our top figure and show here we have our strain element having one axis that is coincident with the principal strain axis. So what are our principal strain axes? Well, they were our A, B, and C. So we can still see we have Z is equal to C here. So we do have that one axis that's still coincident with that principal strain axis, where we can see now our A is now transformed up here to X and our B is over here at Y. So now referring back to Hooke's law, we can show that our shearing strains are zero as well, and also that the principal planes of stress are the principal planes of strain. So with this rotation of the principal axes, this we can represent as well by Moore's circle. So we can come down to the bottom left figure here, and we have Moore's circle for three-dimensional analysis of strain. So again, we take a look, we have our normal strain and we have our shearing strain right here on our X and Y axes respectively. We can see that this outer circle right here from C to A, it's our full diameter right there, and this going from our point O right here all the way out to our point A on our normal strain axis right here. This is our epsilon max, our max strain right there, and our min is the distance here from our O to C right there. And we can see now the same thing here. We have our 1/2 of our max shearing strain is this distance from our axis here, our epsilon axis, all the way up to the outer edge of the circle right here, which is also our radius, and we've shown that governing equation in the previous slides within this module. So as we continue our discussion for three-dimensional analysis of strain, let's take a look at a special case. Our case we want to take a look at here is for a plane strain where X and Y axes are in the plane of strains. For this scenario here, we see that our Z axis is also the principal axis, and the corresponding principal normal strain is represented by our point here that Z is equal to 0, or our origin. So we can come over here to our diagram for Moore's circle for plane strain, and we can see there's our Z is equal to 0, so this Z axis is our principal axis right here. Z is equal to 0 right at our origin point right there. So now let's take a look at our diagrams on the left over here for our possible configurations for Moore's circle for plane strain. So we can look at the configuration on the top left in part A, and this is the principal strains having mixed signals. Now how are these mixed signals? When we take a look at our origin point here, Z is equal to 0 right at our origin there, we can see this point B lies on the left-hand side of this right here. So this is going to have a negative value associated with it, and we can see that from this point here to this point here is our minimum strain, our epsilon sub min right there. Now we can see our point A is lying on the positive side of our origin right here on our epsilon axis. So this is our epsilon max right here, and this is going to be from our 0 origin right there out to our point A. So now part B, this is our principal strains having positive signs. So both having positive signs right there. So we can see everything lies to the right of our origin point. Z is equal to 0 there. So a B is going to have a positive sign associated with it, and our A is going to have a positive sign associated with it. So all of our principal strains are going to have positive signs. We can see here there is no distance between here where there is normally this is off-centered from our origin point. This right here is right at our origin point. So our epsilon sub min, our minimum strain right there, is equal to 0. Our epsilon max goes from our origin point out to point A right here. So our epsilon max is also equal to our epsilon sub A. And we can see that this max distance here, epsilon sub max, is the diameter or 2 times the radius of that circle. So going back to our configuration A, if both points A and B lie on opposite sides of our origin, so there's our origin, so A is on our positive right side, B is on our negative left side right there, so they're on opposite sides of the origin, then in this case here, the maximum shearing strain is the maximum in-plane shearing strain, which is D and E if we look at this here. This is our point E, this is our point D right there, so this is our maximum shearing strain. But for the situation we have shown down here in part B, configuration B, the principal strains having positive signs right there and both lying on the same side, so if A and B lie on the same side of our origin, then this is a case where our maximum shearing strain is out of plane of strain and is represented by our points now D prime and E prime right there. So there's our D prime right there, there's our E prime right there, and you can see this is now our new max shearing strain. So if we recall back in chapter 2, we can say that if we use A and B as the principal axes within the plane of stress and C as the principal axes perpendicular to that plane, then we can say we have sigma x equal to sigma A, sigma y is equal to sigma B, and our sigma z right here is equal to 0. So again, this is recalling back some information governing equations within chapter 2 of our textbook. So now with these and utilizing Hooke's law, we can come up with the relationships that we see here for the corresponding normal strains, which relate to equations 7.55, 7.56, and 7.57 in our textbook. So what we want to do now is take a little bit closer look at these equations 755 and 756. So what we can do is we can add these two together to get a relationship of our epsilon A plus our epsilon B. So we'll do that to the left-hand side of the equation. This is going to be equal to the sum of all the right-hand sides of the equation here. So we can add these all together. And when we do that, we end up with a relationship that we can see that we can pull out some common terms, and we'll end up with a sigma A and a sigma B. So we can then rearrange that relationship and solve for our sigma A and sigma B. So when we come down here, and what we have is our epsilon sub C is equal to a negative Poisson's ratio over our modulus of elasticity times this epsilon A plus epsilon B that we can plug into now. And we plug into that there, we end up with this relationship that we see here, that our epsilon sub C is equal to negative Poisson's ratio over 1 minus Poisson's ratio times now that epsilon A plus our epsilon B right there. And this is our equation 7.57 in our textbook. So a couple things to note. The strain perpendicular to the plane of stress is not going to be 0. And also, if we look back over here at our diagram here for Moore's circle strain analysis for plane stress, if B, right here, our B value right there, is located between A and C on Moore's circle, so there's our A and there's our C on Moore's circle, if B is located in between those, the maximum shearing strain is equal to our diameter CA. We can see, well, that's because we say C to A right there is our full diameter of the circle right here, whereas the radius right here, going from our origin point, our center line here with our epsilon, up to our point D right there, this is going to be 1/2 of our max shearing strain right there. So our full shearing strain, our gamma max, goes this full distance right here, which would be that diameter, which would be the distance from C to A. So next, let's take a look at the measurement strain. How do we physically measure strain? What we can do is we can utilize strain gauges. In particular, let's take a look at some strain rosettes. So these strain gauges are going to indicate a normal strain through changes in resistance. So what we're doing is we're actually measuring resistance changes to whatever type of material that these strain gauges are adhered to. And we can correlate these changes in resistance to strain measurements. Let's talk a little bit about the arrangement of these strain gauges. The arrangement can be used to measure the 3 normal strains, our epsilon 1, our epsilon 2, and epsilon 3. This is called a strain rosette. So the rosette is used to measure normal strains along our x and y axes, and their bisector is referred to as a 45-degree rosette. Now with this 45-degree rosette, our epsilon x and epsilon y are measured directly, whereas our gamma, our shearing strain right here, xy, is obtained indirectly with the following relationship that we can go back to our equation 7.43 in our textbook, and we say, okay, our gamma xy, shearing strain xy right there, is equal to 2 times our epsilon OB, and you can see right here from our diagram right here, there's our epsilon OB right there, which is along our bisector, minus epsilon x plus epsilon y. And we can see how our epsilon y and epsilon x strain gauges are measured directly right there, because those go along, our epsilon x goes right along our x-axis, and our epsilon y goes right along our y-axis right there in this diagram. And again, in this diagram, we can see here along our bisector right here, this is 45 degrees off our x-axis and 45 degrees off our y-axis. So let's take a look at our diagram in the bottom left. So this is our generalized strain rosette arrangement right here. So we can see within this here, we have our x-axis, and we can see everything is measured relative to this x-axis. So we come up here, there's our L1 axis with our epsilon 1, our L2 axis with our epsilon 2, and our L3 axis with our epsilon 3. And we see within each of these, we have our theta 1, which is our angle between our x-axis and our L1 axis, theta 2, which is the angle between our x-axis and our L2 axis, and theta 3, which is the angle between our x-axis and our L3 axis. So with this information that we see in our diagram there, we can come back up here and say that our normal and shearing strains can be obtained from our normal strains in any 3 directions by the following relationship given in our equations 7.60 in our textbook. For example, here, if we wanted to find our epsilon 1 is equal to our epsilon x times the cosine squared of theta 1. So we're breaking this down now into our components here from our x-axis, bring it up now to our L1 axis by this angle of our theta 1 right there. So we have there, and then we have from our y component right there, epsilon sub y times the sine squared of theta 1, and then for our shearing strain in the xy, this is times our sine of theta 1 and our cosine of theta 1. Now we can do a similar type of thing for our epsilon 2 here. Break this down here between our x, y, and our shearing xy right there. So this is saying our epsilon x times the cosine square of theta 2 now, this angle here between our x-axis and our L2 axis right there, plus our epsilon y times the sine squared of that same theta 2, plus our shearing strain in the xy right here times the sine of theta 2 times the cosine of theta 2. And last, for our L3 axis with this angle theta 3, we have the epsilon 3 is equal to our epsilon x times the cosine squared of theta 3. Again, that same angle right there from our x all the way over to L3, plus our epsilon y times the sine squared of theta 3, plus our gamma here, our shearing strain xy times the sine of our theta 3 times the cosine of our theta 3. Now, with these three equations, we can solve these all simultaneously and get answers for values for our epsilon x, our epsilon y, and our gamma xy right there. So each of these are unknowns: epsilon x, epsilon y, gamma xy right there. Three equations, three unknowns. We can solve these simultaneously. Something like this, depending on how many numerical values we have and how much we can simplify this, maybe we can solve these by hand, rearrange and plug one in terms of another to solve those values. Or maybe this is a good one to set up in Excel, MATLAB, Python, come up with a matrix arrangement in order to solve for those by solving these three equations simultaneously. So now let's apply some of this theory, concepts, and governing equations to a practical problem. So let's take a look at this concept application 7.5. Within this problem here, they tell us that as a result of measurements made on the surface of a machine component using strain gauges, so we're physically measuring these with strain gauges that are oriented in a variety of ways. So we've just taken a look within this module at different arrangements that we can use, different theta values for the angles between them. It's been established that the principal strains on the free surface are, and we've measured this from our strain gauges, epsilon sub A is equal to 400, this is positive, times 10 to the negative 6 in units of inches per inches. So this is the units of strain right there. And our epsilon sub B is a negative 50 times 10 to the negative 6 in units of inches per inch. Now, if they give us, and we know our Poisson's ratio for some given material, and it's given to us here as a Poisson's ratio is equal to 0.3, then with that information, what they want us to do is to find two different things. In part A, they want us to determine the maximum in-plane shearing strain. And in part B, what they want us to do is find the true value for the maximum shearing strain near the surface of the component. So now that we've had an opportunity to read through that problem statement and take a look at exactly what they've given us and what they asked us to solve for, we'd then create our setup page if we were going to go through and solve this by hand. So again, recall on our setup page, we want to write everything down very clearly that we can get from the problem statement and the initial given diagram, if there is one, and have it all in one place, organized, ready to go, and everything they asked us to solve for as well. So that's what we started to do at the top of this page right here. We can see all the given information that we extracted from that problem statement we have up top here. We have our epsilon sub A given to us as a positive 400 times 10 to the negative 6 units of inch per inch for our strain. Our epsilon sub B is equal to a negative 50 times 10 to the negative 6 units of inches per inch for our strain there. Our Poisson's ratio is given to us as 0.3. Now they're asking us to solve for two different things. So part A, they want us to find the maximum in-plane shearing strain. And in part B, they want us to find the true value of the maximum shearing strain near the surface of the component. Now from here, what we can do is we can come up with a little bit of a procedure for analysis. So if we're dealing with part 1 right here, or part A within our problem here, they want us to find that maximum in-plane shearing strain. So how can we do this? What's our plan of attack? Well, what we're going to do is we're going to draw a Moore's circle through our points A and B and corresponding to the given principal strains. So now within this here, the maximum in-plane shearing strain is going to be defined by our points D and E, and this is going to be equal to the diameter of our Moore's circle. So let's proceed with this part A and draw out our Moore's circle. So now let's take a look at part A of our problem. So in part A of the problem, it asks us to solve for our maximum in-plane shearing stress. Now we discussed our procedure for analysis for this, and we decided that we're going to use Moore's circle in order to do this. So we're going to draw a Moore's circle through our points A and B. Now these points A and B are going to correspond with the given principal strains. So this was in our problem statement, epsilon sub A is equal to positive 400 times 10 to the negative 6 in inches per inch. And epsilon B is equal to negative 50 times 10 to the negative 6 in inches per inch. So pay attention to our sign convention. This is a negative right here. So now from this here, our maximum in-plane shearing strain is going to be defined by the points D and E. And what this is going to be is equal to the diameter of Moore's circle. So I've done down here in the bottom left is drawn out a generic Moore's circle with everything labeled that we need for this problem right here. So we'll take a look and we'll say, okay, there's our point A. Now our point A is going to correspond to our epsilon sub A right there, our given principal strain, which is 400 times 10 to the negative 6. So I can write that in. It's 400 right there. And then I have my epsilon sub b. Now this is a negative 50 times 10 to the negative 6 inches per inch. So you can see here, my generic diagram, I do this on the right-hand side, and that would be my epsilon sub min right there. But in reality, this is going to be a negative value, so it's going to need to come over here on my left side of my origin right there. So that's what I have now is my b right there is a negative 50 right there. So now I can plug that in. Now I can say, well, if this is negative 50 and this is a 400 right there, then my total diameter is going to be 450. So from that point right there, from my origin to A is 400, and from my origin to B is 50. So this total distance right here, my diameter of Moore's circle is 450. And as I said, my in-plane, my maximum in-plane shearing strain is going to be equal to the diameter, because D to E right here is that diameter, so that is going to be equal to 400. Now I can double check this with our relationship here that our max shearing strain is equal to the absolute value of my epsilon max minus my epsilon min, where my epsilon max goes from, as we saw in our generic one, our origin out to the outer circle of A right there, so that's 400, minus my epsilon sub min. Well, my epsilon min is a negative 50, so minus a negative 50 is a double negative. Pay attention to that sign convention right there. This is the absolute value of that, and this is going to be equal to 450. 400 minus a negative 50 is 450, which is exactly what we found by looking at the diameter of that. So that's a great way to double check. So as we move forward in this course and within your engineering curriculum in general, what we'll notice is we learn that there's more and more different ways, different approaches, and different methods to solve problems. And the further we get along in this, the more of these you'll have at your disposal as resources to go through and use them to either solve it one certain way or use them as double checks to solve them another way and make sure that both ways did work. So that's something we're going to do right now is we're going to take a look at equations 7.50 and 7.51 back in our textbook for this relationship right here for the same part A for this Moore's circle problem right here. So we'll say, well, our average strain right here, epsilon average, is equal to epsilon x plus epsilon y over 2, and our radius right here is equal to the square root of the sum of the squares of our epsilon x minus epsilon y over 2 squared plus our shear strain all over 2 squared right there, square root of all that. So we can go through and start plugging in our known values for this. So let's take a look here. In order to solve this equation here, 7.51, we'll need to plug into these our epsilon average that we'll need from 7.50. So let's go back to that equation 7.50. Look at our equation here and start plugging in. Epsilon x plus epsilon y over 2, well, this is our principal strains right there, which is 400 plus a negative 50, all over 2 is 350 over 2, which is 175. And now we can see our radius here is equal to the square root of our epsilon x minus epsilon y, so 400 minus a negative 50, so it's a double negative, is plus right there, all divided by 2 squared, plus now we have a relationship right here where we have our shear strain xy right there, divided by 2 squared. So we can go through and we know there's two different ways that we can do it. We can take a look back at our other equation and know that our total diameter was 450, so our radius is 225, and we can back out, solve this for our shear strain right there, and we'll find that that is equal to 450. Or we could plug in our 450 right there, and it'll prove to us that our radius is 225 and that our diameter is 450 right there. So that's another way we can double check from that. Then we can move on to our equation 7.51 here, and we can say, well, our epsilon min right here is equal to our epsilon average minus our radius right there. Well, we've already solved for this right here. Let's do a double check right there. Our epsilon average we just found up here is 175, and we found that our radius right here is 225. We plug in for that there, so this is a negative 50 right there. And our epsilon max is equal to our epsilon average plus our R right there. So it's 175 plus 225 is 400. Plug this into that same equation we used before that we gathered before from our Moore's circle. Looking at it, plug these in. It's 400 minus a negative 50, which would be a 450, which is a double check again for our max shear strain. So now let's move on to part B, still looking at our maximum shearing strain here. In this part of the problem, in part B, they want us to find the third principal strain, or epsilon sub c. So since the state of plane stress is on the surface of our machine component as they give us in our problem statement, we can utilize our equation 7.59 in our textbook. And this right here is our 7.59. We saw this earlier in our module as well. We have our epsilon sub c is equal to our negative Poisson's ratio divided by 1 minus Poisson's ratio times this epsilon sub a plus epsilon sub b right there, where epsilon a is our principal strain given to us in the problem statement as 400 times 10 to the negative 6 inches per inch, and our epsilon sub b is given to us as a negative 50 times 10 to the negative 6 in units of inches per inch, and our Poisson's ratio was given to us as 0.3. So this is a straightforward plug and chug to get a numeric value for our epsilon sub c. So we plug that in, we say our epsilon sub c is equal to our Poisson's ratio of 0.3, all over 1 minus 0.3, which is 0.7, times now our epsilon sub a, which is our 400 times 10 to the negative 6, minus here, because it's a plus and negative, 50 times 10 to the negative 6 from our epsilon sub b. Do out our math here, and we see that this is negative 150 times 10 to the negative 6 inch per inch, and that's the negative from this right here, which comes from that right there. So again, sign convention is very important right there. So we get this negative 150, and that tells us that here at point C, there's our epsilon sub c right there. So now what we can do is draw in our another circle right there on the inside of this, and we have this total outer circle right here that now we can see that we have this new diameter for right there from D prime to E prime going right through this right here, or from C to A. And if we know that from A to B was a value of 450, and then over here now we have this distance from O to C right there as a value of 150, and then from O to B is 50. We have all the information that we need to add everything together. So this would be 100, this would be 450. So this total diameter right here now from C to A, or from D prime to E prime right here, is going to be a total of 550. So that is our maximum shearing strain for part B.